Thank you very much for your invitation, your introduction, and for giving me the opportunity to present remotely. So it's now 5:07. I'll be done by 5:30, I think. Correct?
Yeah.
Okay. So there has been a revolution in computer vision and natural language processing using large data sets. And the natural question is this all we also need to do for robotics, just to scale up training data? And there are a lot of efforts in the community that are trying to do that by collecting all possible kinesthetic demonstrations. And this workshop, I think, asks how can we structure planners and learners so that we can do most with the least amount of training data. Before we discuss what we can do, I think one thing is to see where can the training data from robots come from. My favorite way of collecting, collecting data for robotics would be visual imitation. You're just watching of some humans doing the task, and the robots imitates it using few shot or reinforcement learning. And now, unfortunately, this is not what's happening right now because computer vision simply doesn't work well enough. And thus, the most efforts in industry and academia is on learning from demonstrations. For RSS, for example, we had 2 sessions on imitation learning, and most of those focused on learning from demonstrations where actions are provided. Okay. I'm also very excited about building simulation scenes and learning in simulation sim to real that we don't need to discuss today. So what we see is we see large vision language models that are repurposed to also predict actions. These are 4 beautiful papers, Clifford, Palmi, RT1, RT2. All of them are very, famous from Google and from Dieter's group. And basically, the trend is we're going towards robot foundational models using end-to-end instruction and image-to-action mapping with large transformer backbones and lots of demonstration training data. One question we asked is most of those representations try to relate 2D image features to 3D motions of the end effector. And we said, can we do better if we use 3D scene representations directly as opposed to images and 2D images and 3D actions? By 3D scene representations, I mean, can we use the information about depth and camera pose, okay, to relate the scene with the robot gripper? Our first attempt was in Coral 2023, where we presented ACTA 3D. Now, before that, of course, there are other beautiful 3D robot policies like PERACT and RVT. RVT actually showed up also in Coral 2023. But let me tell you what ACT 3D was trying to do. Okay, it was trying to act in 3D, as the name says, but I just want to give you a little bit of the details. So the idea is that you have a robot that has access to 1 or more calibrated cameras that have also a depth sensor. So you sense the world from those images, which you featurize them as you see here. And then you lift those features to 3D space using the sensed depth. So what you have here is a set, it's a graph, a set of 3D tokens where every token is a patch 2D feature vector in a corresponding XYZ coordinate. Okay, so we call this a 3D feature cloud. That's all you have. Now, what you do is the goal of ACT3D is to build a 3D action map that will describe where the robots and effector should be in the next time step, condition, of course, on the visual 3D feature cloud I just described, but also in an instruction, right? So it's a multitask policy. You swap here the instruction, and it can predict where the robot gripper should go for different instructions. The reason we were trying to build a 3D action map, as opposed to just regress directly in the XYZ coordinate of the end effector, is because we believed in action equivariance. We thought that the 3D action map is a much better representation if we manage to preserve locality of computation. Now, the problem with 3D action maps is that they need to be very, very highly accurate. So they need to be super high resolution, which is very difficult to do in 3D. Okay, so all attentions on very, very fine-grained voxel grids are extremely expensive. So what ACT3D does is it learns an iterative sampling of where the end effector should go. So here I try to show the iterative sampling. Here is a closed up visualization of this. First, we sample a coarse 3D grid, and we call those sample points ghost points. There is nothing on those points. These are just XYZ coordinates that are though featurized. We compute features for those. So this is a continuous scene representation. You feed an XYZ here, each of those points an XYZ coordinates, and there is an attention, a 3D relative attentions that compute the feature for that location, and they are trained to with the standard classification loss. Is this location where the end effector should go or not? And then what we do is you threshold here where the end effector should be, and then we go and we sample finer around the heat of the previous 3D map, okay? And then again, finer and finer till we say here is where the end effector should go. And then we regress its orientation. So because of this iterative classification objective, we can have multimodality on the 3D action map, the translation of the robot and effector, but unfortunately the regression is still, the orientation is still regressed, so there's no multimodality there. It's just a deterministic prediction. Despite that, ACT3D did score very high in RL bench. RL bench is this benchmark now, it has been transformed to Colosseum, even larger. In RL bench, essentially, you predict key poses, and then you link key poses using motion planners. That's how it works. And as you see here, thanks to this better representation, I mean, okay, there are two RL benchmarks, depending on which paper you're going to read. Here is we do better than HighFormer, and here we do better than PERACT. And interestingly, our model with 10 demonstrations does better than PERACT's model with 100 demonstrations, which shows that, you know, in the low data regime, 10 to 100 demonstrations, architecture matters. And we did some ablations. So this is the best part of the paper that shows that when you have those 3D representations, you can change the camera location at test time, and you're going to suffer a drop in performance. So you'll go from 98 to 74. But in comparison to 2D policies, they catastrophically fail if you just move the camera around. So you get this viewpoint, essentially equivariance, if you reason directly in 3D for free, without need to train for it. Of course, pre-trained features matter. Here we use the clip pre-trained backbone. I don't think we played enough with alternative pre-training, but just to say that, you know, every image is featurized, and large-scale 2D pre-trained features are used in the architecture. Now, unfortunately, as I said, the orientation is regressed. So the next thing we asked is, can we handle multimodality both in translation as well as in orientation? And we are inspired here by, of course, nowadays we do have extremely accurate, you know, high-fidelity generative models that do not drop any modes and do not hallucinate modes. So they're extremely accurate. So the idea is, of our next work, which we call 3D diffuser actor, is to combine these 3D scene representations that I just described with action diffusion instead of this iterative sampling and so on that I just described, okay? So the architecture now becomes much, much simpler, and it looks as follows. Again, you have a robot that looks at the camera, has a camera and a depth map, and it featurizes again the image and leaves the features in 3D. So again, you have a 3D feature cloud. You can aggregate for multiple viewpoints. So this part is the same. But now there is no sampling of ghost points. The only thing that happens is you also add some tokens. So you can, let's call each one of these feature vectors a scene token. So you have a bunch of 3D scene tokens from sensing the images. And you have, of course, some language tokens here from the instruction. And you also put some tokens that represent the future and effector trajectory. Every time step of that trajectory is a translation and then orientation. And depending on this translation, this XYZ coordinate, again, essentially every time step of that trajectory becomes also a 3D scene token. So both the robot gripper and the scene are reasoned in the same 3D space. And what we do, we feed this into a big denoising transformer, and we predict back the noise. And there is a very important detail here that this transformer has 3D relative attentions, so not absolute attentions, which means the absolute XYZ coordinates of the scene tokens is never shown to the network. So why? Because the center, how we choose the center of the coordinate system is an arbitrary decision. We don't want our model to overfit to that. And we don't want to do augmentations to handle it. So this is by design, the network is robust to that decision in this way here, okay? And then at test time, what you do is you sample your gripper locations from white noise, and then you iteratively denoise them to predict the trajectory. And here I'm showing samples of those future trajectory samples. I'm not showing the orientations because it would be very awkward to show. So I'm just showing translations in Kelvin. And here I'm showing the key pose samples. So we don't predict trajectories, we predict one key pose here, the future key pose. And you see that because during demonstration collection, the students sometimes picked up the green grape or the red grape or the dark grape. The diffusion model captures all those three modes accurately. So you see the 3D diffuser actor does very well, both in Kelvin and RL Bench, much better than our previous work here in RL Bench Act 3D. Better also than here other previous works. Our chain diffuser is also something from our work that didn't work well, again, due to the fact that the Act 3D predictions were not accurate here. But also better than another method that was presented in RSS 3D diffusion policy that in principle has the same ideas, being in 3D and being in diffusion, but does not essentially merge the 3D scene tokens and action tokens the way we merge them, like they condense everything into one embedding vector. So this does not preserve, unfortunately, the spatial locality. Okay. So we did some ablations to figure out where the performance boost comes from. And you see that if you go from 3D to 2D, you suffer a dramatic loss in performance. But also if you remove the relative attentions, again, you suffer a loss in performance. Now, I'm not sure if you do a dramatic number of augmentations, if you can get the last one back, but you know, I mean, why would you not design your architecture to be translation equivariant in the first place? And the one thing I want to point out is that 3D policies doesn't mean that you have access to multiple viewpoints. You can still have access only to one viewpoint, but you reason in 3D. So here we see that 3D diffuser actor does much better both for Act 3D as well as from GN factor, which is another method that uses a single viewpoint, but is trying to densify the 3D feature grid by, you know, training for feature completion. Again, the same pictures of RL Bench, and here the same things in the real world. And the code is available online, and I hope you can check it and use it if it's easy to, you know, if you find it useful for your projects. Now, the question is, how can we do better? Somehow, learning from kinesthetic demonstrations is not very, I mean, it has the following drawbacks. It mixes language understanding and execution, and it can only be trained from demonstration data with actions. Right? But we have an incredible amount of passive video data on the web that don't have actions. But guess what? The world moves the same, both for the robots and for us. So we should be able to learn how the world works just by watching passive videos. So we've been trying to think the following question. Can we go from language and image to some sort of sub-goal that we can train only from observation data, only from videos, and then going from sub-goal to actions, only learn the second part from kinesthetic demonstrations. You see, we have two neural networks. So the first one on the left will be learned from observation data. Only the second part will be learned from kinesthetic data. And the question is, what should be this sub-goal representation? And I'm pretty sure in the era of large video models, the first thing that comes in mind is image sub-goals, okay? We can, given the current image and the instruction, we can feed this into a video model and predict a future image, a future RGB image, and then have an image conditioned policy to predict actions for us. And indeed, there are some works that I truly like a lot. Susi, Yilundu is part of many of them that capitalize on the fact that, you know, video models are good and they're only going to get better in the future. So why don't we use them as simulators of the world to predict sub-goal for us And then we will use inverse models that take the current image and the hallucinated future image to spit out actions. And we can learn that inverse model from kinesthetic data. And when I say kinesthetic data, I mean also teleoperation data and anything that gives us robot actions. Now, the problem with video models is that they are not really causal. I mean, they predict the next sub-goal, but because they reason in the pixel space, very often they hallucinate. Now, this is as of, July 2024, things in the field change super fast. It's very hard to predict what's going to happen and where the solution is going to come at the end of the day. But in any case, what we are exploring, one thing we're exploring is use sub-goals in terms of point trajectories. So then we have one high-level policy that is trained supposedly from passive videos, and we need to go from videos to 3D point tracks. So this is like we have some perception works that try to do that. And this part doesn't require any actions. And then we condition on the hallucinated point trajectory to predict the action. So it looks a little bit like this. Now, unfortunately, here you see only the future point tracks of the gripper, but we also reason about the point tracks of the rest of the scene. And this does well in Calvin, so this is just a proof of concept. This is something that we're working on right now. We're just still exploring how we can get those sub-goals from passive videos. Another solution that people, researchers really like is to go from a complicated instruction, like move the blocks into mismatching balls, into other less complicated instructions. So they consider sub-goals in language space. And language models have been absolutely phenomenal into breaking longer instructions to reasonable sub-goals. Now, there is a grounding issue here that language models don't see the scene. Now, of course, you can use a vision language model, and it's probably going to do a better, more grounded, at least, and relevant prediction of language sub-goals. But this makes sense, and there has been a lot of works in doing this in natural language. They break sub-goals in natural language or in Python code. Okay, and here we have code as policies here bottom left. That also was the best paper award in ICRA 2023 as of the best learning paper. Okay, which I found very astonishing. The beautiful long prompt and how they really pushed, whatever could be done within context, essentially LLM prompting. So we are excited about this direction. One limitation we see is that, the context window of LLMs is limited. And also if you, very much how they decompose an instruction into sub-instruction very much depends on the in-context examples. Very oftentimes, if you give irrelevant in-context examples, they're going to make mistakes. So the idea here is very simple. What if we give them an external memory that it's a key value memory where the key is a natural language and the value is the decomposed plan. And then based on the language and vision context, they go to their memory, retrieve the relevant examples, put them as in-context examples, and then use those to predict the plan. There are a lot of benefits of having such an external memory. One of them is that you can learn new plans very easily just by storing them. Here is an example. You talk to your agent and you say, make me a duck sandwich. You should have such and such and such. I add this in memory. Then tomorrow you tell me do the same thing, but don't put lettuce or mayo, etc. And the language model can automatically not only remember the plan because it has external memory, but also adapt the plan, right? So we have essentially a very modernized version of task planning that is much stronger than symbolic planners and can handle free-form natural language, which I think is pretty astonishing. We've been working on doing task planning and language parsing for so long, and now language models give us only, I mean, not for free, but quite for free. So this method does well in those benchmarks of Alfred and Teach and embodied question answering and so on, simply by having one memory that saves all these instruction and plan examples. So you have one memory across all those tasks without any in-domain training. This is zero shot. Okay, so the language model is not trained and nothing. You only populate its memory. All right. And of course, we also evaluate of how well it can handle changes on the original plans. Now, the problem with language sub-goals, at least the way they are right now, and this is, of course, an active area of research, is their lack of grounding. They are not directly visually grounded. If they stay in pure language space. And here is one. Depending on the prompting, you may ask me to put the strawberry to the right of the apple and in front of the green ball. And I'm not be able to find that I need to put it in between the two, okay? So I may simply fail if I just do one command after the other. So the last work I want to discuss is the following. It proposes to use sub-goals, not in image form, and definitely not in point trajectory format or language format, but rather in terms of object graph abstractions. For example, here we have a graph of all these little objects making a circle. So it says, go from language into simpler language. That's fine. We have language sub-goals, but ground those sub-goals using generative models over object graph arrangements. And, these generative models, much like Georgia described earlier, they can be composed. And this is also, Yelund very often talks about the composability of those energy-based models. And this composability now will allow us to come up with object graph compositions simply by composing the corresponding energy-based models. And, once we generate the final object graph, and then we're going to use an inverse model to, pick and place the objects to the right final locations. So an energy-based model, you can think of it as a neural network over, the input is essentially locations of the nodes of these object nodes, right? It's a graph configuration, and the output is a scalar value, and that scalar value represents the energy, which is low if the graph satisfies the concepts, here square, and high if the graph does not satisfy the concept, okay? And through that energy function, we can essentially, we defined a distribution using this normalized negative exponential, and we can train, if we have this energy function trained, we can sample object graph configurations compatible with this concept, starting from some initial random configuration and following them negative of the gradient, okay? And adding also a little bit of noise. So this is so that we don't get stuck. This is called, this procedure is called Langevin dynamics. So you see here what I'm showing, we start from some random node locations, and then the nodes go to their final circle configurations. Now you may say how we're going to train those energy functions. Well, you're going to train them not from kinesthetic data. You don't need to have actions. You can train from simulation data where you have some objects that satisfy some concepts, right? You only need to have these bounding boxes of those objects. So you go through abstractions. I can give you a circle over cell phones, and then you can make a circle over spoons, okay? Because you are abstracting from the details of the object, and you only keep the bounding box and its centroid. And the way we train is that we take samples that are actual training samples and try to minimize their energy, and then sample from our model and try to maximize the energy. So here is our energy-based model library, and the only reason we didn't use diffusion models is that this work was developed before diffusion models become, let's say, popular yet. So we go A left, right, A on top, below, and we also explored using the same object graphs in 3D as opposed to 2D. So here you see them in a bird's eye view configuration, but you can also consider them in 3D. So here is make a line, and here is make a circle. And then here is the beauty of compositionality. Imagine you have this set of objects, which I see some apple and orange, and then some lettuce and plate, etc. And then I give you this very complicated language instruction that you break in language sub-goals using a language model. That's the right way to do it. Back then, what we did is we trained the semantic parser using programmatically generated training examples. Now you can do it training free simply using an LLM. And the output of the parser will instantiate an energy, which is going to be a summation over individual energies, okay? And each energy will be over a graph, which is a set of objects. And here you see that all those energy concepts are all pairwise. And, there is an object here, which is the plate that is involved on, let's say, multiple of those energy terms. So what you're going to do is you're going to take gradient, you're going to initialize your object locations and then take gradient and update them directly following the negative of the sum of the gradients of the energies. And you're going to come up with a configuration that actually satisfies all those concepts Yeah, and this is what we say, this is a compositional, the compositionality. We ground essential language compositionally through those energy-based models. We call the system scene reorganization through energy minimization. So the whole system goes like this. You say the complicated language, this goes to a parser, and today's parser is a language model that essentially tells you what objects you need to detect and what energy-based models you need to instantiate. Then you need to detect those objects. There's no way around that. You need to run an object detector, and here we fine-tune our own beauty jitter grounding, language grounder. And then you essentially sum the energies for all the energy-based models, and every object node will have different number of energy terms will affect it. So you'll predict the final locations of the objects, and then you will use some very simple pick and place policies, image condition. We use clipper type of policies to do the rearrangement. And because you have all those abstractions, there's nothing end-to-end here. You don't go end-to-end from image to action as in the first part of the talk. You can dramatically generalize from simulation directly to the real world across any types of objects and so on. And of course, this works on incredible amounts of composition simply due to the compositionality of energy-based models. Yes, and of course, it does much better than anything out of the box without any training, much better than even trained, end-to-end language to action policies. Yeah. Now, so the interesting thing is, as I said, you can run it now directly in the real world. Why? Because detectors generalize. You don't need to fine-tune your detectors to work in the real world. We can detect objects quite reliably nowadays. The energy-based models generalize because they operate over abstractions, and the action policies also generalize because they're very local, okay? And so you can go in front of the robot and say, rearrange all the small objects in the circle inside the plate. So you have your detection. Here is the energy-based model that has two terms of being inside the plate and the circle. And then you have the robot doing the pick and place. So this is the end. What did we discussed about 3D scene representations and translation invariant being important for generalization in learning from demonstrations. We showed that retrieval augmented language models can remember plans and adapt plans. We can ground language subgoals to generative models over object graphs. And we can compose those generative models for planning under multiple constraints and multiple language subgoals. So thank you very much for your attention. These are the students that are behind the work. Chunwei and Nikos worked on 3D diffuser actor. Ayush and Nikos on this EBM planner that I discussed. Gabe on the retrieval augmented models. Zian and Theo on ACTA 3D. And looking forward to your questions. Thank you.
Thank you for the nice talk. In your title, you mentioned manipulation and imagination. And I saw manipulation and I saw a little hallucination, but I didn't see imagination. So what do you mean by that?
Yes. So we call it imagination because in the last part of the talk, when you tell me put all the objects inside the plate, I don't just start from the current configuration and start moving around the objects. I imagine the final scene configuration where the object should go. Now, I don't imagine it in pixels. I imagine in an abstract level of object arrangements, but first I imagine it and then I go ahead and act. So I call this imagination.
You mean the robot imagines you? Said I.
The machine learning algorithm, yes, through this composition of energy-based models.
Hi, Katerina, this is Georgia. Thank you for the great talk. I was wondering how much the approach of the 3D diffusion actor and then later on the hierarchical method is affected by the registration of the cameras. Do they play a role? It doesn't matter wherever the cameras. Second part is, could you envision being to a single camera setting, like an embodied camera setting, where there's only one view?
Yes, this is a very good question. And I think there is this misconception that 3D requires multiple cameras. You can do everything from a single camera, but you just need to have this camera registered with a robot. So basically, this robot's 3D coordinate system, which from what I have discussed, it is very, very possible. And this is the case in,
In this
embodied.
case, did you take the point cloud or the single RGB and you integrated multiple views of this single camera?
Here is a single camera, and that camera has an RGB and a depth sensor. It's an RGBD camera.
Thank you.
Okay, so if there's no further questions, let's thank the speaker and we can start the panel discussion.